if we now look into it, at least it should, yeah. So you see it overwrote just everything, and we overwrote a bunch of more memory with 999, which we shouldn't have. But this simply demonstrates that there really is no protection within a C++ application. If you start writing at memory addresses, you can overwrite anything with anything and create arbitrarily hard to debug bugs. So it's very important to, whenever you're accessing memory, to try to ensure that you are not accessing an invalid address, because often it can work without a crash, but it will cause a crash later on once something tries to access this data, which then will be completely invalid. So what we can do to avoid that? First thing we can do is, well, one thing we can do, a very important feature of C++ is the ability to have a so-called constructor and a destructor. So these are two functions. So the one has the same name as the class. The destructor has the same name but prefixed with a tilde. And the constructor will be called whenever an instance of this class will be created, by either by defining it on the stack or by using the new operator. And the destructor comparably will be always called whenever the function the class gets removed from the stack or we delete it explicitly from the heap. So we can maybe add some hash include std so that we can make a printf, and then let's write printf make class and let's call it new. So whenever each of the function is called, it will write this into the console output, and then we can put our class here into a scope. And let's make here f test2. Here print test1. Okay. And when we run it, whichever window is this one, the right one. Okay, I forgot the new lines. So, but you see that it wrote test. So this line was executed. Then, once the class got actually created, it printed this. And then when we went out of scope, so when we closed the bracket within which the class is instance is defined, it automatically calls the destructor, which wrote this text, and then we had our print test2, which was after it. So let's first fix that by adding our new line characters, and then we can try to do the same thing but without using a scope. Instead we use just a pointer to start with, and we use a new operator, then here delete class. So with new and delete is like malloc and free in C, just in C++. You still could use malloc, but of course malloc will not call you the constructor, and free would not call you the destructor. If you really need to use some sort of custom memory management, with C++ you can. Basically, then you just need to manually call the destructor on your class before freeing the memory, and there is a syntax for the constructor to call it without making it allocate memory, so just that it will directly invoke the constructor on whatever memory you have provided it as a pointer. So this can be also done if it's desired, but usually you probably will not need these abilities. So it's possible as said, but I don't think that you would use that for anything in your career. So yeah, that's that. We can also step through it. Well, first maybe we should try actually running it and demonstrating that it actually does what I said it does. So as you see here, oops. Yeah, it wrote test, then it made new 3, and then it wrote test 2. So it behaves the same way. And the important thing is that if you would have in your class some members of the type of another class, this will also call then the destructor for those. So you can have quite a complex object. For example, let's create another class, my class 2. Give it also a constructor and destructor. Class 2, class 2, class 2, create class 2, create class 2, and then here you will make an object of type class 2. And now if we run the test, it will have invoked both of them. Oops, what I forgot. Ah yes, we need to make it public. Suck. If you look here, and it's interesting because as you see, it first did class 2, then it did class 1, and then the freeing was in the opposite order, which in a way makes sense, because at the moment where you arrive here in this constructor, you expect every member variable to be already set up, and analogously, if you are in the destructor, you expect every member to still be valid. So that's why you have this particular order. And this mechanics can already be used to implement something quite nice. So let's do that here quickly. New, we can use a new class. Let's just go with new my item. We will just create a header file. Let's call it my array. Okay. Sorry. Class. We call it my array. Public. Protected, and let's create some array. So let's say we want an array of integer type. So let's call it int check m. Then we need a constructor and a destructor. Oops. We want int size. We want to tell it how big it should be. Yes, and we said we want to do everything in the header. So let's do everything in the header. So here make just like new int size and delete array. So when you can use the new operator also to create whole arrays of objects, in which case you specify the size in square brackets, and for the delete it is intended that you always use this empty brackets to free an array. In practice, forgetting to do it will work as well, but it's not what the standard tells you to do, and some compilers may actually screw up something if you forget to do it the right way. With Microsoft's compiler, it seems it's sufficiently idiot-proof that you can do things that are not allowed to be done, and it will somehow manage to still handle them correctly. But this is not something one should rely upon. So here for now we have a very simple object where we create it and give it a size. So we can use it here. Let's create. Should we turn this off? Yes. If 0. My array 100 elements. Let's put that in a scope again. Okay, maybe we should actually put this prints here and here because we will always want to see them, and we need of course to include our new object, my array. Yes, and the nice thing is that once we are, can say the breakpoint on the delete, Continue. So when we enter it, it will first run, of course, the constructor. And then when it goes out of scope, the constructor. Then when it goes out of scope, it calls the destructor. And I think I did not implement everything. And then it clears. I think it did the constructor twice, which is not good. Yeah, no, it was fine. Sorry, it was fine. Everything in order. And such a strategy would allow you to avoid of forgetting to free the array, because you can have stuff here like let's add some more printfs, and somewhere in between okay, let's also make some variable int x is gleich 1, 2, 3 if x so 1, 2, 3, then so we can even have a return from the entire function, and so then we will not even ever reach this test2, but we will still reach the destructor. Was it complaining? We need to return a value. So we are in the constructor, zack. Then we reach the destructor, and then we don't reach anything else because we terminated the function. So you see we have test1, test. As you can see here, and this part didn't happen because we returned, but still the destructor for our array was called. So this is a very useful strategy to avoid creating memory leak, so you cannot forget to deallocate the array. And the next thing, of course, that can be done to avoid writing to invalid memory is, instead of trying to access this array member, we can write a function. Let's call it ball. Oh, and we should remember how much size we have. Without, let's use a large s. Without, of course, knowing the size, we could not check whether the size is valid. So boolean set at int pos int value if pos is smaller 0 or pos is greater equal size, return false. Else is equals value. Oops, the array at pos is equals value, and then return true. And then we also need our int get at position. We don't have a value. If this is not true, then I don't know, return. We have to define some value for what is to be returned if it's invalid. We could go with -1 or 0. Let's go with 0. Or else we return the value at the position. So now, if we would only use those two functions to access our array, we can effectively avoid ever writing past the boundaries of the allocated memory. So we can quickly, of course, demonstrate it. So here punkt set at 99 value 1, 2, 3 and value 100 and test1 and test2. If we step through it, we see that in the first case it does the assignment as it should, while in the second case it will just break and return the false result, such that at this point we could write an error or something. So for example, if this is not true, printf error. So you see already the very basic functionality of C++ allows you to do quite a few nifty things, which allows you mostly to mitigate whatever dangers the use of just plain raw C++ would have. Of course, if you want to pass this array to some other function, for example the file read function, which does not know this type, you would need some function to be able to access the array directly, and then you would of course need to ensure somehow externally that the function which you give this pointer to will know how many bytes it is allowed to write to it and not write past its end. But at least for your own code, using such helper objects is very helpful, obviously. And the next thing that you can do with classes is you can also create a class which is which has its features, and then which derives from another class and adds the features of the other class to its own. So let's create that. This is called a derived class. Let's call it my class X. We need to say which access the parent class will have, so we say it's also public. Then we give the class name of the parent class, and here inside this we can create a new constructor and destructor if we want to. We don't well, yeah, that's already one thing that will be problematic. So we will see in a second a live demonstration of a bug and the solution to it. Right here, so here again we put our two lines that will tell what's happening, and let's say we add a new another function, myfuncx. My class myfuncx, and since this was far2, well, we could make the first one override the first variable, and our function here override the second one. So you see we can access, we cannot. If we put something as private, even a derived class cannot access it, but if we put it as protected, then derived classes will in fact be able to access the variable. So here, now when we check, we can access it. I mean, we could leave this one here as protected. Yeah. And now if we run it, you will see that the order will be, what will it be? It will first run the myClass2 because it's a member of myClass, then it will make the constructor of myClass, then it will make the constructor of myClassX, and then it will do the same thing just in reverse order. So here we can comment this part out. We create now an object myClassX, then we want to delete that. We want to print something in between. Let's call it, okay, let's leave it at 2, and this will be test 3. Okay, so as you see, we first do the constructor of the member class, then of the parent class, and then finally of the last class we have. And then when we do the delete, the things happen in reverse order. And an important feature of this derived objects is that you can in fact assign pointer, let's call it 1, is equals pointer. You can assign to a pointer of the you can assign to a pointer of the parent class a pointer to the child class, because this child class contains everything that the parent class also contains. So you can use everything from it directly. So here, so while on pointer, let's call it pointer 1 and pointer 2. And let's comment this out for a second. So on pointer 1, you can access myfunc and I don't know, 1, 2, 3, and myfunc2. Wait, did that? myfuncx, sorry, not myfunc2. myfuncx. While on the pointer that is only of the parent class type, you can only access myfunc. because at this point the thing is oblivious to the existence of the other functions of the also of other properties. So we could of course add here some other variable. We could not access it anyways, since it's since here it is protected. But as said, you can access those this way. So here you can access this func2, and if we run this and keep a look in the debugger, we will see that in pointer1, is it hanging? Is it waiting for something? Yes, it's waiting. Okay, so that once it does that, we see that here both these two values have been adjusted, and of course this was ignored since it was the same object. So maybe we should put the pointer here first, so that you see that first the content will be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and when we execute this on the other pointer, it will of course change here our first variable as expected. And then one issue in which we will run when doing things like this is if we make delete, if we call delete on pointer2, you will see that it will not longer behave correctly. You see it did not invoke the destructor for the myClassX case. It did the destructor for myClass and myClass2, but it forgot to call the destructor for myClassX. And to avoid such problems, what we can do is we can use a feature of C++ called virtual functions. And we will first do it with the destructor, and then we'll implement another virtual function. So here we write virtual. Oops, I have a typo. And we only need to do it for the first function in the base class. We don't need to do it for in the derived classes, because if the compiler sees that it is already virtual in the parent class, then this will also be virtual. But it's elegant to also do it. And now, even though we called the destructor, well, invoke the delete operator on the pointer to the parent class, which as such should not know anything about the extensions in myClassX, it will still in fact invoke the destructor of myClassX properly. So we see here it invoked the destructor as it should. And now we can let's make another function virtual as well. So let's make myfunc here virtual, and then we can implement myfunc in our derived class, and it will work. So if we would have not make this virtual, whether this function or this function gets invoked would depend on which type the pointer is. So like with the destructor, if the pointer would be of class of type myClass, without virtual we would always invoke this one, and with virtual we will always when the type is in fact of the type class X, then it will invoke this one. So let's give this function a function body. Virtual needs only to be specified in the header. It cannot and should not be specified in the C++ file. And what we can do from here now is we can in fact call the myfunc of the parent class by first typing just the name of the parent class, and then arg1. And let's say inside this function we want to also write to variable 3, well, maybe the same argument, why not? Or maybe let's take the opposite of that argument. So now if we have here our pointer2 on which we call myfunc, when we put a breakpoint here and enter, we will see that we'll end up still in the X case. So you see it worked. We ended up in the child class despite the type of pointer2 just being the normal class. And then like this we can access the parent class's implementation of the function. And once we are done with that, we can then do some own code. Or of course the order here is arbitrary. We could also first do our own stuff and then call it, or if the function would be returning a value, we could do something internally depending on the value. So that's fully flexible up to whatever you want to do with your classes. There is no real limit how often you can derive classes. What you also can do is you can in principle derive a class from multiple classes, but that we should not do yet because that's just gets messy. What you also can do is you can define a function as purely virtual, so basically one that you don't provide an implementation for. So let's do that. Sorry, that's a different language. So if you want to make it virtual on in C++, virtual int. If you want to make it abstract in normal C++, you just write virtual function, then you write is equals 0 and strichpunkt instead of just strichpunkt. So just strichpunkt would mean so just semicolon would mean the compiler will expect the function to be implemented somewhere in your CPP file, and if you try to compile this, it will just throw an error. But if you write is equals 0, then it will ignore the fact that this function is missing. But of course, in your derived function, you need to implement it, because if you don't, then it will not work at all. So we can do that, and then we can see what happens if you would try to. Okay, okay. So if we run this, we should use it at some point. So we can use, for example, the parent pointer here. It doesn't matter. What was it? My test func. Yeah, and when we run it, it compiles and we enter directly in our child function. Now, if you have a class which has such virtual functions, you are not longer able to just create an object of this type. If you try that, you will see the compiler will complain and say that my class cannot initiate abstract class. And the idea is that it should even tell you which one. Yeah, here it tells you. In my class test function is abstract, because you are not allowed to have a function without that is like dangling, not connected to a real function. You can only have that when you then later derived something from. So this strategy can be, for example, very useful if you want to create some base class which should just provide an abstract interface without then caring for implementing any variation of this interface. So you just write a lot of virtual something functions, and then whenever you actually create a implementation you will derive it from, you will provide all the functions that are missing, and then you can use this object as an argument for other of your functions somewhere in code, which will only understand this abstract interface but don't care for the implementation. So there are many examples. For example, you could create a general object which represents input and output operations, and at this point you would not care whether you are writing to the console, to a file, to a network socket, to a pipe, or some other device type. And then for each of those types of potential I/O objects, you would implement and you would write an explicit implementation, while other functions which then just take this object type as a parameter will then be very generic, because they will not longer depend on this being explicitly a pipe or explicitly a socket, but as long as it's of type I/O object, then you could use it. So we can, for example, implement maybe something very simple of this sort. So let's create a new class. Let's call it abstract IO. It doesn't have a base class. Yeah, that's fine. So, is it clear until this point, this classes and this derivation of subclasses? Or are there any questions at this point? So you have a normal class, just an object like you would have even like a struct in C or something. But in C++ you can create another object which will inherit all the properties of your parent object, plus it can add own properties. So if you create an object of type myClassX, it will include everything that already was implemented on myClass, plus whatever you add here. This way you can easily extend classes with additional functionality. No, everything is copied, but you cannot access private variables. If it's private, you cannot access it, but it is still there, but it's not accessible from your functions. You need some access functions like this ones here to access it then. Okay. Yes, if you don't have a accessor function, then you cannot change them. One, yeah. So functions you put everywhere, wherever you need them. It is customary that you put variables only in private and or protected sections, because you usually don't want people to access variables of your class publicly. But functions can go everywhere. Now making a virtual function within the private section might be not very reasonable, because then you cannot access it anyways. But making virtual functions in protected sections is very useful, so you can do that without any limitations, and of course in public sections as well. Because then if you derive so you can then derive a class which then can override those functions with own functions, while these functions will still not be accessible from the outside of the class. So if you are in some other class somewhere else, then you still cannot access them, but if you make a child class, then you can access it. So for example, if you design something where you want in special circumstances to allow someone to access something internal, then you would put everything in protected, and then this, if the guy or girl trying to access this protected resource knows what it's doing, then they have to just derive a class, make an own function which is public, which then will internally be able to access this protected resource and change it. So instead of locking down that thing in a way that is completely not user-friendly, let's say, you lock it down in a way where you can exclude any accidental access to things that might be problematic, but you still allow a proper non-hacky way to access it if it is necessary to do so. Okay, so two more things maybe about these things. So first of all, you can have as many private and public sections as you want. I mean, normally of course you can write many different variables into one. A, B, C, but you can then have again a private section, and you can have again a public section. As many as you want. There is no limitation, at least no reasonable limitation. So if you would like introduce like thousands of sections or even thousands of variables, at some point the compiler will bug out saying that it only can handle 65,000 members or something like that. But that's usually are limits which reasonably no one will ever reach. So for all practical purposes, you can have as many of them as you want and mix and match them as you like. Of course, the most elegant way would be to have something public at the top, then have some protected in the middle, and then have just private stuff at the end. But that is just up to one's taste. It is not technically relevant in which order this sections are presented, etc. What you also can do is you can allow another class. So let's do this here. Let's make here a function, a protected function. My func. Let's just keep it here since we don't need anything for it. And now we want, for example, my class to be able to access my func, but only my class. Or there can be more than just one, but we don't want the general public to be able to access it, but we want to allow my class to access it while we are not related to my class. So we can write friend class, my class, and if we do so, then my class will be able to access all protected members of my class too. So this is not then specific to just the one function, it will just apply to everything that's protected. So it is not a very fine means of accessing stuff. What was the name? My2, I think this was my2 Oh, how did I call the variable? Large M. My2. Now you see we can access my func, despite the fact that it is defined private and in a class which is unrelated to us. In principle, you can use this. Where was it here? Syntax also with a function name. So if we define here our class and try accessing something, oops, we cannot, but we could try to say that we want this function to be our friend, and then we can access it. So this much to that. Usually you would probably not do it with functions, just with other classes, but if you need to, you can. Good. So we wanted to make this abstract IO object. So we would have this, then we make it we start with public, then we have our constructor, and we should call it C abstract IO. So we have our constructor, we really don't care for any content for it. We have a virtual destructor, also without a content. Then we will start with our abstract function. So since it's an IO class, you would probably want to have something that will give us the potential size of the data. Get size. For this we can implement a default body, which just says return 0, because not all types of IO objects in fact have a size property. Some of them are just streams, so you can read from it until it's until you read everything. But this does not mean that it's empty. It just means that there are no data yet. New data may arrive at any point in time. But of course, what we will for some of them, just get size may have no meaning. So we give an implementation such that you don't need to implement it in the child class. But other operations like read and write will be fully virtual. So let's say virtual int read. This will have like some buffer and size, and this will be virtual. Write will also be virtual, and that would be the very basic that a basic IO can do. It can read, it can write, and that's it. I mean, it might be useful to have a function that will tell us if it is at the end, so if there is nothing more to be read. But that's already like a advanced feature. So for now that would even be already enough. And since we are lazy, we will just use the same file, and let's implement a couple variations of this. So let's make class C file IO, public abstract IO. So we will, for now we'll just add constructor and destructor to everything. Let's see if we will use it. Then we need the functions which we will actually implement. So that goes here without this. Abstract IO, file IO. Oops. Return 0. Or rather, let's return an error. -1 is a nice value for that something is invalid. Because if you read or write, you obviously expect that you can only read or write a positive number of bytes. You cannot read or write a negative one. So if you return a negative value, this indicates an error. You could actually also use for size -1 to indicate that size is not a valid argument for this. And of course, if it is a file, then size for a file would be a valid parameter. So in this case, we would actually want to have a body for that as well. But since we are lazy, we will not implement it yet. We'll just put it on -1. And now, to contrast that with something else, let's create something that reads and writes, or just writes, even something that's not able to read from the console. So we are lazy, we just copy this thing again. We just call it then C console IO. We will definitely not need this or that. For write, we can here return -1 because oh, sorry, for read I wanted to make it for read, because we don't want to implement read function from the console. We just want to have a write function. And of course, if those start to become more complex, then putting all of them into the same file will be a huge mess, and you should ideally maybe have just a abstract IOH without a CPP file, and then 2 pairs of files of a source of a header and source file for file IO and for console IO separately. But for now, let's just be lazy. For a better separation, we can just use comments. So let's make some nice comment. File IO, zack, zack, and console IO. Okay, and our console doesn't really need anything more except the ability to write. So let's say put C, where was put C defined? I guess stdio, like everything. Stdio, put char, yes, wait, character file stream F. Can't we do that only with consoles? Does it only work with files? That should work. Would assume that should work with everything, not just no, that will probably be only for the file. So we would either need to specify a proper file descriptor for the console, or we just use printf. Let's be lazy. So we want a for and to make printf %c. This is a way. So we should use a function that really just prints one What is it complaining about? That only really puts one character at the output at any point in time. But let's be lazy. Because put C would really work only with a file stream. So we would need to find out which stream actually represents the local console. That would need another few API calls, and that just makes things complicated. So let's just stay with this simple implementation. And for our file, it's of course more difficult because we need an ability to open the file. So we now can do a few things. We can either give a file name in the constructor, and whether we want it to be opened and in which way, or we could make a dedicated open function that will just open it if we ask it to. But let's be lazy and demonstrate it this way. So const, that should be const char asterisk path and const char asterisk mode. Can provide a default argument for that, would be R. So by default we just want to read a file. Yeah, so we will need to implement this as well. Oops, that's almost right. We need to remove the brackets, and we will be implementing the destructor properly here for our file IO as well. Now the default arguments should only be present in the definition, not in the implementation, so we remove it. Okay, and we will need something that's protected, and we need here a include stdio h file. Oops, yeah. Okie dokie. So here file ist gleich f open path and mode. Oops. If you Control C on in a line where nothing is marked, it will then just copy the whole line. So this is not always what we want. Yeah, and if this fails, then file would. So if fopen fails, then file will be will be null, which is just a placeholder for 0. So here we can test if this is not null, then was it f close? Yeah, f close, and we close the data stream. Now with size, we can also have a check. So if this is equals null, then return -1, indicating that whatever we tried failed. So if you would open a non-existing file for writing, the file will be created, and then we could properly get the size of the file, which then would be 0. So we, as said, use -1 to indicate that there is something wrong. What was that? fstat? I think it was fstat. Okay, I don't remember what was the explicit. So there is a get file size command in the Windows API, but we want to get the file size just using the standard library. And there was another function for that. I just don't remember what it was called, since I haven't used that one for a long time. I think I know what it was. It was double L, maybe? Yes. ftel. That gives us the size of the file, I think. Let's quickly check that. Ftel returns the current value of the position. No, that's the wrong thing. That returns the position, but we want the size. Okay, there might not be such a function in fact. So in this case we need a elegant solution. So we take so So this returns us, this ftel thing returns us the current position in the file as a well, that is interesting. It says it is just a long. That would not be good, because this would mean that we are limited to 4 GB of file size. Let's see what it does. No, but it really is just a log. Okay, then our function will be limited to 4 GB large files. So we get the files current position. Then we set fseek file, comma, offset null, comma, origin. What was it? Fend, seek end was it. So we want the end, then we make again tel. Corpus and last position. Then we make fseek from the beginning again, seek begin. There must be, I mean, if we would be using the Windows API, there would be a better way. We just use the, is this not begin? Set, okay, then set and begin. If we would use the Windows API, there would be a quick query, but this super old stdio library, which is available on pretty much every platform, obviously doesn't have Windows API since it is also available on Linux, DOS, and whatever else one might imagine. So it's apparently missing a few useful things. The trick here to get the position is we first save where we are in the file right now, then we tell it to go to the very end of the file, then where we are will be the size, basically. And then we restore wherever we were before we tried to check the size. And that's it. Actually, I should maybe comment that, but let's do that later. So we have our size implementation. For read, we can just use fread with the buffer. And then we have element size is 1, element count is size, and file stream is our file. Oh, I broke my own guidelines. I should have called that mfile. Yes, okay, mfile. And that should, as far as I remember, then just return us the amount of bytes read. So if we, so in principle we could just return the value of whatever this is, and fwrite will be the same. Fwrite works the same, although with write we could make this const to indicate that we do not intend to change the buffer. Actually, that would be elegant. Of course, then we need to fix that everywhere, here and there. Okay, yep, but that should be working. So let's first see if it will compile. But it, okay, wait. What was it? Underscore s. Okay, this one has a different syntax. Reference s, file name. Okay, why they want it differently, who knows? I mean, that's documented somewhere why they still have an s function for this. Data loss, these are all warnings, else. Yes, that demonstration, we should turn this off, since we could remove the one thing that makes it abstract. And this must return a value. Oh yes, it must. Let's just return size. Yep. Perfect. So if we comment out the next part, Now let's create some instance. We need to include that thing first. Abstract IO. C console IO and C file IO file. So path will be I don't care. Test takes. So we can use a relative path, and as mode we want to write v. Don't care for anything else. Let's do v plus. And now let's make a function which will take a say abstract IO asterisk IO as an argument, and now we can pass both of those objects we just created, will point us to those objects, to our writer, and despite those both being completely different objects with completely different internal implementations, for the writer it only means the only meaningful thing is that the IO thing has a read and write, and they get size. In this case we only care for write, and we can just write some string. Oh, that's good. We can demonstrate also at this opportunity another nice feature. We can implement something on the abstract IO that will be using the virtual functions which do not exist on it. So let's call it write string. And the difference between write and write string is that write string takes a buffer and expects a null character to terminate it, so it does not need the size argument. This is smart enough on its own. Abstract IO. Okay, now we would have two ways of implementing that. Let's go with the more elegant one. Int size is equals stren of buffer, and return write buffer. And now sure, we could in principle just copy this and put it here. Yes, we are missing something. String h contains stren. Yep. So now in our writer we can just make IO write string and then test123 \n and then write a few things. Yeah, why not? And depending which object we gave to it, let's just step through this really step by step. We will first end up in our abstract class, then we'll end up in one of the specializations. So here we go in, we are in the writer, so we are still in our initial code. Now we enter the write string function here in our abstract class, and then we enter the appropriate write function. So apparently console was the first one, so here we will be looping through that until we are done. So let's just make a breakpoint and skip to the breakpoint, and then we return from this thing, and then we of course would repeat the whole thing until we are done and exit. So here now for the file case we enter the exact same function, we then still enter the exact same function, but now we end up in a different function. And voila. And now on the console we have our 1, 2, 3, and somewhere how did I call that? Where did I save the file? Output. Test2, and in our okay, we have not. Oh yes, sure, we did not close the file yet. We need to press continue. Now we can open it. and here it also has the 1, 2, 3 test. And the nice thing is that here usually of course you have to call fclose on your file, and here the destructor of our class of our cfile IO class automatically, once it goes out of scope, will take care of that for us, and return our and make the fclose. One more thing we should probably do is that if this is not valid, we should always return -1 here and here, such that if we fail to open the file, when we try to write, we will get a appropriate error, and not well, that thing will then also throw an error. Just depends on the documentation which one. Although I guess it will probably just return 0 because it didn't read or didn't write anything. So this, in that sense, is better to have this with -1. So that would be a demonstration what you can do with abstract classes. So I guess this is already quite a useful thing. And as said, we could also have like a pipe IO and socket IO, and so on and so on and so on. So if we are writing a program from scratch, this would be something we could include into it. Of course, if you are using some larger framework to do so, for example like the Qt framework, there in fact is a huge in fact are such things already pre-implemented for you. So in the Qt framework you have, let's open a notepad, you have QIO device, from which you then have Q file, Q abstract socket, Q local socket, that's a pipe, oops, Q local socket, then you have Q network socket. I think you have Q network socket, or does it go directly to no? What is TCP socket derived from? That is loading. Okay, there is no network socket in between, it just goes directly to TCP socket. UDP. So these are both network. Let's see what else is derived from that. Only those two. Anything else derived from? Okay, QBuffer is also derived from this. QFile device, local socket, network replay, and a lot of other things. Even QProcess is derived from an I/O device, because every process can read and write console, and for some reason they found it useful to be able to do that with processes using this wrapper. But the idea simply is that such a generic I/O object can really contain a huge amount of different. Oh, and local socket is, by the way, derived one level higher. So Qt is not something that we will be looking into in this lecture. It will be something in part 2. It is a huge framework which contains all the nice things already implemented, such that you can start writing the relevant code and don't need to spend time on writing such basic things. But it's of course important to understand how those work. So this is just a short detour at the edge. One thing that might be interesting is this QBuffer. This is not a device or anything, this is just a piece of memory. So the idea here is that you can write to memory the same way as you would write to a file or to the console. So let's say C buffer IO, and that sounds like a interesting thing. So this we'll put here for later. And buffer IO will be something that will be a homework. So What do we want? We can implement it in two ways. One way is that it gets a predefined size, and then just always keeps the size, and you can write until it's full. Or or another option would be that it gets an initial size, but you can write past its end, and then it would grow. So let's say growing is optional, main size is not. So int initial size, comma, bool can grow is false by default, but it will not be false. Wait, what is it complaining? No, it's not. Fine. We need the size, of course. Get size. It can read and it can write. It will need a few things, so int m size und Stern array accurate data. Then let's give the user the ability to access the data, even though that might be dangerous. Okay, of course, first we return size. We should make get that's const. Oops. Stern get data returns data. So we return it as constant, such that the user at least is not too much enticed to change it. Oh, we need a few more things. We need to be able to set a position. Void, or not void, or boolean. Seek int position. Actually, maybe we should be more reasonable and use size t. Oops, small t. Size t for this for all those sorts of parameters. But then let's stick to the int because we use int at the top. The nice thing about size t is, would be that would have a size which is platform dependent. So it would be 64-bit if we compile it for 64-bit, but for our test cases it doesn't really matter. So we have seek. Realistically we will need here some more things. Int m underscore. Yes. So let's copy that part. Buffer IO. So this goes away. This one is already implemented. So seek needs to be implemented. Read, write. Okay, method -1 to do implement. To do implement seek return false. To do implement buffer IO also to do implement, but it doesn't return an error. This should not be set. And let's use this opportunity to demonstrate one more thing you can do. You can, but that also works already normally. So you can overload the function, meaning you can provide a function with the same name, just a different argument list. And then, of course, depending on which one of the constructors you call, then our compiler will pick the right one for you automatically. So it has the same name, but it has different arguments. So this one, oops, this one I will implement. No, I will not. Jawohl. So homework from the 12.05.2022. Yep. So buffer IO 1. I know what, maybe we should not make things too complicated. I will implement one of the constructors, but in a way that it will not help much. So you can call another constructor of your existing constructor by just writing its name and providing the argument. So this constructor will then call that one. This one will allocate the memory we need, and we here just mem copy our surface destination m data to our m data from our m buffer, the amount of size bytes. Yeah, that is easy enough. So the constructor you can pick, I think it's double L. Analog. Appropriately, okay. 2. Implement the destructor. You can pick whether you want to use delete or free, it's up to you. Since it's a basic type, it doesn't really make a major difference. Then we need seek, read, and write. Okay, and one thing here. 3. Let's be a bit more helpful. It's obvious that we will need at least a m position variable. Right. That will keep track of where we are with our read and write operations. So that is that. Okay, and then for implement read. Operate safely and implement fear write to operate safely. It was a large D and BNF. That is explained. And optional. Can grow like true, comma. The required size, resize accordingly. That should be more explicit. The data will be resized to I don't have a good sentence to make the tune to a valid offset. No, it's not correct either. Resize to make the position point To the next valid offset in the array. So the way position works, it probably also should be explained, and we also should have here a get position function. Int get pos get position. Right here. So the way the position pointer works is that it points to the location of the next operational file. So if you have an empty file, the pointer, the file pointer will point to the offset 0, because if you would try to read or write the file, you would try to read or write the file at offset 0. So the idea is that if you would seek and can grow as true to a position which does not yet exist in the array you have, then the array should be resized sufficiently such that position -1 will already be a valid offset. And of course, whenever you write to the array, and you see, oh, I'm going to write to a position which is already not longer valid, so where we don't have a memory, then it needs to resize the array, and then the write operation can succeed. And the next optional thing, optional 2, will be that whenever you resize the array, you will resize it by more than what is needed, such that you don't, such that if you write single characters to your array, you don't need to resize it each time. But for example, let's say we want to grow it each time by half of what it already is, such that we don't like double it each time. Array resizing to either grow it by doubling it or to grow by 50%, or by, let's say by XX% to be configured. Yes. So maybe one more hint to do that. The get size function on the actual feature of the data and not the size of the over provisioned array. And it should be implemented such that if you grow the array past whatever initial size it had, that then when you grow it, let's say by a factor of 2 each time, and then you request the size from the array, that it will not give you just the total array size including the yet unused area, but it will only give you the size of pretty much the last offset to which a write operation was performed. That I should probably write as well, because that makes it more clear. So yeah, that's, I think, helpful, because without that last sentence it was kind of not sure, like if you jump somewhere and then write just things somewhere and have a large area over which you jumped over without writing to it, whether you want like the whole thing up to wherever you finished writing, or if you just want the size of what you wrote without the area which you skipped. But now it's clear that when you start at 0 and then you write things somewhere, and maybe even have areas which you never write to, what we want as size is of such an growing array is the last index to which a write operation was performed. And last, I mean the biggest one, not the last like in chronological order. So if you then go back and write something at the beginning, we should keep the largest index as the size value. Okay, that is, I think, a very good homework. It should be easy enough to do. You have already some demonstration of how to do those things with the myArray stuff, at least a very small basic example. And yeah, and it demonstrates and it uses in a very nice way all the capabilities of C++ that we have seen today. Are there any questions at this point? Mm-hmm. Yes, I will do that. Any more questions? Okay, if there are none, then in the last few minutes we can take a look into a few more things that we can do with C++ in order to moderate what things can and how be accessed by the programmer. So we go back to our my class. Let's, for example, add something here. So we can add constant variables, for example. So const let's call it mconst int. A constant variable, like with normal C, cannot be changed. At least it's not supposed to be changeable. And you will now see that here it's complaining it in the constructor. The reason is that since the variable cannot be changed, but it doesn't have a value, so we are kind of in a catch-22 scenario. The way out of it is that the constructor takes something as so-called a initialization list. So after the constructor name and the brackets, you make a double point, then you can write a variable name, and then in brackets you can write a value. And then for the next value you make comma, I don't know, this one for example, fm6, and then you continue with commas and more commas and more commas. So okay, let's go with A and then go with B, C, D. That's enough. And the constraint does not apply in this initialization list. If something is not const, then you can just write to it in the body of the constructor. So D is equals I don't know, phi from 6 again. D. I think we had like up to F E. Did we have an F? Yes. Just fine. But to const one. So if you would try to write the const thing here, the compiler will of course complain immediately that this is not permitted. And this is quite useful in various scenarios. So you want to have some number that is defined as a variable, but you don't want to change it. And even if this would be now a public variable, so we could make this even public, you would not be able to change it from the compiler directly. Of course, if you do a cast on a non-const int and then try to change it, then sure. But these are things that you do consciously. So you will not by accident take a reference on an int, cast it to a non-const int, reference it again, and then assign a value. So that needs intention. While just accidentally assigning something to a const variable, if it's not const, that could easily happen. So that is one thing. What we can also do is we can define a variable as kind of the opposite of const, mutable int, let's call it mvar. Now you might wonder why we would need to make something mutable if it is mutable anyways. Well, there is a reason for that. Namely, when we are in our main class, not here, where we are using things, and then we uncomment this thing. I think if we uncomment this thing, we'll run into an error or not. Let's see. Okay, it's fine. So if we uncomment this thing and then make a pointer of something, you can also make a const pointer. So we can make a const pointer, c pointer c from pointer 1, and now on this const pointer we should not be able to change things anymore. Yep. So while the IntelliSense was not smart enough and it still showed us the variables. It showed them to us because it didn't know what we want to do with them. So if we want to assign variable 1, it doesn't work. While if we would use the non-const pointer we had here, pointer 2, assigning variable 1 would be just fine. Of course we could work around this by casting and stuff, but we don't want to do that. Instead what we do is, if we have defined a member variable as mutable, this means that it can be changed even if the pointer on which it is being accessed as such is defined as constant. So in these scenarios, mutable is helpful. And what we also can do is we can define a function as const. So let's say void. So for example, our get function here, that's already a perfect example. Our get function here, since it doesn't change anything about the content of our class, would be a const, or could be a const function. And the main constraint with such a function is that if we make another one, let's call it void const function, that it is not able to change variables. So if we try to assign this 1 to 3, the compiler will not allow us to do that. Of course, if we remove the const constraint, then it will be fine. But if we add it again, then it's not. And of course, if we would now have a mutable variable, we could still assign something to it. So this is where this mutable keyword comes in very handy. An example which we might take a look later on where this would be helpful could be, for example, if you have a synchronization object which allows you to access one class from multiple threads in a orderly fashion, so that you will not break things by randomly accessing things while other things are accessing the same things and writing values and then dropping them because they end up in the cache and not longer not in your memory. To avoid such problems, you have synchronization objects, and such synchronization objects can be defined as mutable, such that you can access them even from a getter function. Because even if you are getting a value from a class, if this is a more complex class, you would want to get a consistent result, and so you would not want, for example, if you have an array with 3 elements, right, and then you have one function which then would always return a copy of these 3 elements, and then you have another function which would run in a parallel thread which would write an element 1 at a time. So at this point, when you at some point in time take the 3 elements, the other function may have just written 2 of them and did not yet update the 3rd one. Then you would get an inconsistent result. And to avoid such things, you can use synchronization objects, so you can lock them before you do your access and then unlock them, so that when the writing function, which updates the elements 1 at a time, before it starts updating, it would lock this synchronization object, then it would do its updates, and then it would release the lock. And our getter function, when it is trying to get a copy of this object, would also first try to get a lock. But if it tries to get a lock on something that is already locked, then the function, the whole thread will be suspended by the operating system and only resumed once whatever other function just had the lock, which other thread had the lock, releases it. So this way you can introduce a defined order to your operations, at least keep the operations atomic, so that you cannot get a from in between result. And such objects, it is useful to be able to define them as mutable, such that you can operate on them from within your constant functions. And another keyword you can use is static. let's call it mStatic in the type. And what this is a in principle it's like a global variable, but name-wise, from the point of view of namespaces, it is associated with the class, so you cannot access it like arbitrarily, but you still need to put it somewhere. So while all these other variables we have here live in the memory block that is allocated for the class, a static variable will need to be explicitly placed somewhere. So for example, we can place it here. We write in the class name static, and we assign a value. So this variable will be located within by the compiler in some writable memory region of the process, and all the classes that try to access this variable will all access the same instance of this static variable. This can be useful in various scenarios as well. One such scenario could be if you are creating a class which is referred to as a soliton. This is a class of which within any application always only one single instance exists. So let's do that maybe quickly. But of course it's not like the compiler would in any way enforce this. So you could of course try to create a second instance, but ideally you would try to do it in a way that would not allow you to do it. So let's create a new class. Let's call it mySoliton. Okay, so we have our class. We need a constructor, of course. It should be a C, mySoliton. Then we make public. Might need a well, let's say this one doesn't need a destructor. Then we make a public function, which is public static. So functions can also be defined as static, and this means that a static function does not have access to any variables except the static variables, because it is not associated to a class object in memory. It only can act on whatever static members this particular class had. And here this function will return a pointer to a Soliton object, and it will be called instance. We could also call it get instance. That is rather up to us. Let's keep that for implementing later. Then we need some private member, which we will call static. Oops, it's a typo, static extension instance, and that is all we need. That is a small function. Now obviously would normally add something to this class to do. It is boring if it doesn't do anything, but that's already enough. So Soliton, that's the type, that's the location, null. Then let's see the constructor. The constructor doesn't do, well, there are different ways to implement it, but let's let this one don't do anything. And then we, oops, that is wrong, that needs to go there. Okay, and now our instance will first, why is it complaining? Null is undefined. Well, that is not true. Null should always be defined, although it might be undefined. Okay, and then we include stdio, then it will be defined. Right here. So here what we do, we check if this is null. If this null, then this is like new. Then we call our constructor, and then we return our object. So now if from wherever we are, let's go back to our CPP test, let's include that. So if we now want to access our Soliton, we would do it like this, instance for example like this, and we can access the object, and this is a static function accessing a static variable which calls the constructor, and so on and so on. now you might think, okay, what if we just try to create a soliton here? This will not work because the constructor is not public, and it even tells you that you don't have access to the constructor. So using this permission mechanism, or this access mechanism, and not making our constructor public, we ensured that the only thing that can actually invoke our constructor and create a instance of our object is our instance function, or actually maybe I really should call it this getInstance. Doesn't matter. Only our instance function, which then is implemented internally such that it will exactly once call the constructor for the first time it is invoked, and never again. So this also demonstrates quite nicely that in C++ you can, by a smart use of the mechanics of the objects, implement various restrictions and limitations which you might want to enforce on your objects for later use. And we will see more of such limitations in future. So for example, you can make an object being non-copyable, so that you cannot make a copy of it. Or that usually you might then of course provide some function that will create you a duplicate, but the whole point of making it non-copyable is that if you don't implement the copy constructor on your own, the compiler will just use a default copy constructor, which will just like for a struct copy the memory as a block. And this might often not be desirable, because if your memory as a block contains pointers to things that needs to be deallocated. So let's take again a look on our array example. So here, if you would just make a duplicate of this, then for this duplicate we would call, first for the original we would call the destructor, and then we would call the destructor for the duplicate, but then it would refer to the same memory. So if we would want to make our array copyable, then we would need to to create a appropriate copy constructor, which would not, instead of just stupidly copying the memory of the object onto the new object, instead may actually create a new array inside the new object, then copy the data over, and however many sub elements we might have, they all would then be appropriately replicated. There are more additional features of C++ that we shall take a look in during the next lecture. So for example, what you also can do is with these objects you can make them behave like in some way like a standard type. So for example, you could define an object which you call myBigNumber, which would then be, let's say, a 256 bit long number, and you would internally implement its mechanics, and then you could implement operators such that if you then create a few variables of this type, then you could operate with these variables using plus, minus, equals, sign, and all the other operators that you might know from the standard types. But instead of just using instead of using standard CPU instructions, the system then would call a function which then implements your addition. And of course, if you are working with an object which is not longer of a type that the CPU can natively handle, you will need to provide a proper implementation that will need a few steps. So, for example, in part 2 of this lecture, we implemented a big integer number class, which could operate with arbitrarily sized integers, which is, for example, useful in cryptography. So often when you do encryption, you need to work with very large numbers, and the CPU as such cannot do that. So we implement some object that will be able to represent a number of arbitrary size, and then this object will internally implement all the needed operators in a way that all the operations can be executed on any given CPU. So that's to that, but that we will take a look on. So operators and things like that we'll take a look on during the next lecture. There are a few nifty things that you can do with operators. So for now, today, we only have 19 minutes left, so it's not enough for that. But one thing that I can show you is also quite nice. So first of all, when we are within some class somewhere, within a function, for example, we can still define a structure. Upset. Test. So you see that it works just fine. And in principle, we could also just define a class within a function. Where can we? Actually, that might complain. No, it's fine. And of course, what we also can do is we can put a class into another class. So here we have our my class, and we can within it, let's say in the public space, let's say here, create another class. Let's see my class 1, and this also works fine. My class 1, that's the constructor. We don't want it to do anything. So now you might wonder how you would access such a class which is created within the namespace of another class. Well, this is quite easy. First of all, when you are in the class or a class derived from it, you can just write it and voila, it works. But if we are outside of it, we can write my class double point my class 1 and then the name. Of course, if this class would be protected, then you could not do that from the outside. That is. This this strategy is often used if you need some internal objects within your object, which you don't want to expose to the user of your object. Then you just create them internally as private or protected, and then you can access them and use them from all of your internal functions, but they can no longer be used from the outside. And C++ has another mechanism that allows you to do something similar. It's called namespaces. So we can test that as well. Here, let's create a namespace. Yes? Yes? No, it's to define a variable str of the type of the current structure without wasting an additional line of code. So normally you would write type and then the variable type, variable name. But here, if you define the type, you can directly after type, before you put a semicolon, write a name, and then you would have created a variable of this type instantly at wherever you are right now. Not globally, within the scope where you were when you did that. So in this case, it would be only within this one function. Yes, it is just a shorthand to save one line of code. And there are scenarios where this is useful. So if you would need some helper structure, which you don't even want to assign a type to, you could write struct, then curly brackets, then your member variables, and curly brackets, and then the variable name and semicolon. And then you basically created a variable which has this structure, but the structure doesn't even have a name. So might be useful in certain scenarios to save a few letters. Okay, so to continue, in C++ you can create an own namespace just by typing namespace, and from how you access it, it is very similar to a class. So you just, if you want, so let's put a function in it, int my func. And if you want to access this function in the namespace, you just write, let's do it at the top here. You just write your namespace and 2 double points, and then you can access the function. As simple as that. And you can in fact nest multiple namespaces within each other. So namespace 1, namespace 2, and you can of course put also a class here. So you could also access my class. Actually, we couldn't give it a static function. public static static int func. So my class double point function. So you can this is quite useful if you are creating libraries or stuff like that and you want to avoid the aforementioned named conflicts with other people's classes and objects. Then you just put them into such a namespace, and within your code you of course have no conflicts, at least you should not have any conflicts. And if someone else includes it, it will be within some namespace, and then if someone else writes another library with hopefully another namespace, you will not run into conflicts even if the stuff within will be called with the same names. What you can also do if you are too lazy to type MySpace all the time, you could write using and then the namespace name. Or was it without a semicolon? That needs to be outside the function. That needs to be global. Using namespace. Why is that complaining? Or was it using namespace? Yeah, okay, it was using namespace, sorry. Probably that would then now even work within the function, yes. So you write using namespace, and then you can drop the first one, because the thing will assume that whatever you're trying to refer is either global or in that namespace. And of course, once we are in it, we could use using namespace too. We could even drop that. But of course, at some point, if we do this too often, we will probably end up in some name conflict at some point, because usually there are reasons why people would put things into namespaces and other namespaces and so on. And since we are talking about namespaces, the probably most commonly used namespace is the std namespace. So we can use that, which which contains a lot of useful functions. So for example, include string. Normally you would need to write std string, but if we are using namespace, we can just write string. And string is a class provided by the std standard template library, which represents a normal ASCII string, and it takes away all the pains of using strings in C, because now you can just at any moment in time append stuff. One thing that it is missing, unfortunately, it doesn't have a format option. So if you want to fprint something, you cannot fprint to a std string. But there are other things you can do. We can take a short look on it. Std stream. What was it? Streams. What was the correct name for that? Was it streaming? It was streaming. It was IOStream. And actually it's already included here for the sample. So std IOStream fee. The IOStream is for the other thing. So IOStream is such a general class, like our abstract IO. What was it? Was string writer in the own object? Std string. Std. Just have to find the right name for that. There was a function, there was an object which you could use to create strings quite easily from so a good replacement for printf. Since this is I'm usually using Qt, so I don't remember how this was named correctly. It was either Streamwriter or something like that. Mstream std stream. It does not seem stream what was that? String stream, that's the right name. Yesterday string stream, do we have that already included? Yes. Yeah, well, and we can give to it, right, we need to give it a name. Let's call it as string stream stars. String stream, we have to give it a string as argument, to which we'll be writing. Oops, that is a small s. And now we can just where is it complaining? Oh, std. That's a stupid typo. It's not yet happy. It doesn't need. Actually, okay, it doesn't need anything. It will return us a string once we are done with it. So. Why is that complaining? That should be working. String. I think it's not properly included. I think we are missing some include to make that work. I think we have only a abstract definition. Where to include that from? String include. It's always a good bet to just try to the name of what we of the class as such. Nope, but it doesn't work. String stream in C. It might be in IO stream. No, but we already included IO stream. S stream. There it is. Now it's working. And you can use this bit shift operators. They are abused by the std library often to allow you to add variables, well, values of any kind to a string. So you can have a string, you have a double you can mix and match as much as you want. We should make a space here. And at the end, when you are done, you just call the string, and then you will get a nice string with all those. Yes. Did we define the function without a body? Yes, we did. And it needs to return a value. Suck. Is it waiting for? Yep. And here it created us the string we wanted in this way. So this is in a way even more convenient than a printf. Although with printf you can easily format the strings, while here you would need to first call some function. What was it? G count, float field. I don't remember. One of there are some options where you can configure how it will handle whatever you print to it. Formatting. width. So for example, you should be able to set width, but this is only, oops, this is only a function. We can provide the new width. So if we make 1, then it should I guess cut the some part of the 0 commas away. Nope. That will be precision, sorry. So we can do a different thing. We can make width to 10 and make precision to 1, or let's make precision to 2. So width should then ensure that we will get longer additional leading zeros or stuff like that. Or what did it do in this case? Okay, so it always adds spaces. That is mildly helpful. And it changed our display from normal notation to the scientific notation. So there are quite a few things that can be configured about this, how this works. But you would need to read the documentation, which can be found here, to use it properly. There are also a few flags that will allow you to specify, I guess whether it uses the scientific or the dot notation, and the precision value just by default change that to the scientific one. But other than that, it's not as convenient as printf. In some ways, this string is extremely helpful because, as I said, you can, for example, also concatenate strings with each other. So you can just write something like that. Oops. Blah blah. Or you can define another string. Startsize gleich blob. So if you know Python or Visual Basic or any of the more higher level programming languages, then this way of working with strings you already know. But with normal C strings you cannot do anything of this. But the ICD implementation of string allows you to concatenate them easily. You can find things. So index, what was it first index of 1, 2, 3 int pos is equals. So you have a function to search in the string. You can have you can remove things. Can you? Does it delete? No. So there should be able to. Or was it erase? Was erase. Yeah, so we can specify an offset. So let's say we want to erase something at position of 1 to 3 of the length 3, and let's say we want to insert at the same position because the position is still valid because it's the first character. And offset count pointer string abc. So as you see, it's extremely powerful and allows you to do many things with the string that with normal C strings would never ever be possible without a lot of handiwork. So especially so what you can easily do with C strings is just edit them without changing their length or moving things unless you copy everything around. And here all these operations are taken care for you by the implementation of string, and you can easily modify them. And since it's 5:30, we reached the end of the lecture for today. If you have any questions, you're welcome to stay and ask them. Otherwise, you can go off to whatever else you have planned for today. Yeah, I will upload the video and the homework. This thing I will upload as well, although it's slightly unstructured, so maybe I will restructure this a bit. And yeah, that's it. Bye bye. Yes?